Hey everybody, welcome back to chemistry. So in the last three play posits, I described the different kinds of interactions that you might find between molecules. So what I want to do is I want to sort of summarize these interactions, but then I want to take our knowledge and apply that to a practice problem. So if I can increase the slide. So one thing I want you to be able to do is identify the three different kinds of intermolecular attractions that are found between molecules and covalent compounds. So the first one we went over is something called dispersion forces, and these are very weak forces that are found in all molecules. Now, the next one up here is something called a dipole-dipole interaction. These are stronger than dispersion forces, and they can be found in polar covalent molecules. Then finally, we went over something called hydrogen bonds. And so these are a bit stronger than dipole-dipole interactions. They are found in a certain subclass of polar covalent molecules. And the polar covalent molecules must have a hydrogen bond donor and acceptor in order to form hydrogen bonds between the molecules. So another thing that I'm hoping that you'll understand is that there are different strengths of these intermolecular forces. And so here we have a nice chart from the book. And so on the left side of this chart, we have the weakest forces. And then on the right side of the chart, we have the strongest forces. And so here we are charting the forces that we went over that occur between molecules of covalent compounds. And so the first one we went over were the London dispersion forces, and so these are very weak. And then we went over dipole-dipole interactions, which are a bit stronger. And then finally, the last one we went over were hydrogen bonds, which are stronger still. Now you have to keep in mind that sort of off the chart here are ionic compounds. So ionic compounds, the ionic bonds between the ions and ionic compound are very, 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 very strong. So let me just write in capital letters here, strongest. So strong est, E-S-T. There we go. Okay, so we move on. So the next point is I hope you will be able to, from a Lewis structure, predict what forces exist between the molecules for that compound. So in order to be able to do that, you'll have to be able to draw the Lewis structure correctly. And then you're going to have to analyze the Lewis structure and determine whether the molecule is nonpolar or polar. Furthermore, if it turns out to be a polar molecule, you'll have to figure out if it has hydrogen bond donors and acceptors. And then finally, what you're going to have to be able to do is order molecules in terms of increasing melting points or boiling points. So let me give you a guide on how to do that. So again, you'll have to draw Lewis structures for these molecules that you're analyzing. And the rule is this: if the molecule appears to be a small nonpolar molecule, it will only have dispersion forces. And those molecules tend to have the lowest melting and boiling points. Now here, this is kind of a point that you have to keep in mind. We've only been really talking about small nonpolar molecules, but you can have relatively large nonpolar molecules. So an example of that would be oil. And so one of the things you probably noticed about oil is that it's a liquid at room temperature, even though it's a nonpolar molecule. And the reason is that when nonpolar molecules get larger and larger, they have more surface area. If they have more surface area, there's more places where dispersion interactions can occur between the molecules. And if that occurs, then you can have a great number of them, and they will raise the melting and boiling points of the molecule. So large nonpolar molecules can have somewhat high melting and boiling points, but for test questions for this class, we're only going to be dealing with small nonpolar molecules. Now, if it turns out you have a polar molecule, you will have dispersion and dipole-dipole interactions. And these molecules will have higher melting and boiling points than small nonpolar molecules. And then finally, if you have a polar molecule with hydrogen bond donors and acceptors, they have dispersion, dipole-dipole, and hydrogen bonds, and will even have higher melting and boiling points. And then again, this is sort of to point out, if you figure out that your compound that you're dealing with is an ionic compound, it's going to have very, very high melting and boiling point. So let's go ahead and try a practice problem. So this problem reads as follows, that we're going to place ethane, whose molecular formula is C2H6, fluoroethane, whose molecular formula is C2H5F, and ethanol, whose molecular formula is C2H6O, in order of increasing melting point. And it's possible that this table of electronegativities could help you out. So if I can go ahead and reduce the slide. So here I have the three molecules, ethane, fluoroethane, and ethanol. And what I've done is written out the correct Lewis structure for these molecules. So in order to figure out the order in which they have increasing melting points, what you're going to have to do is analyze these Lewis structures, and you're going to have to figure out first if it's a nonpolar or polar molecule. If you figure out it's a polar molecule, you'll then have to figure out whether it has hydrogen bond donors or acceptors. The reason why you do all these things is because that tells you the kind of interactions that will be found between the molecules. So as I kind of noted earlier, if it turns out to be a small nonpolar molecule, then it only has dispersion interactions and will have a relatively low melting and boiling point. If on the other hand, it looks like it is a polar molecule, but without hydrogen bond donors and acceptors, then it will have dipole-dipole interactions and will have a melting and boiling point that will be higher than a small nonpolar molecule. And then finally, if you look at a molecule and you can see it's a polar molecule with hydrogen bond donors and acceptors, then it'll have dispersion forces, dipole-dipole interactions, and hydrogen bonds. And then compared to the other ones I just mentioned, we'll have the highest melting and boiling points. Okay, so let's go ahead and analyze these Lewis structures and see what kind of molecules we have here. So here we have ethane, and so the first question again you have to ask here is, this ethane molecule I'm pointing to here, is it a nonpolar or a polar molecule? And so I think you probably know at this point that you kind of have to look carefully at the bonds in the molecule and sort of understand what the electronegativities are of the atoms of the bonds, and then figure out if the individual bonds are polar and nonpolar. So let's do this analysis now. So carbon here has an electronegativity of 2.5, and hydrogen has an electronegativity of 2.1. So here the difference of electronegativity between carbon and hydrogen is only 0.4. So the bond between carbon and hydrogen would be considered a nonpolar bond. Now, this carbon has electronegativity at 2.5. This carbon also has the same electronegativity. So the difference in electronegativity is going to be 0. That classifies the carbon-carbon bond also to be nonpolar. So here we have a molecule that has all nonpolar bonds, and therefore it is a nonpolar molecule. Okay, so if it's a nonpolar molecule, the only interaction it will have with neighboring molecules, say in a solid or liquid state, is going to be a dispersion interaction. And so you will recall that these are the extremely weak interactions here between nonpolar molecules. Now, there are going to be, of course, a number of dispersion interactions between these molecules here, but the thing is that these molecules are pretty small, and so these dispersion interactions don't really add up to much of anything. And so these molecules will have a very low melting and boiling point. So with ethane here, it has dispersion interactions. Now, this is not a polar molecule, therefore it doesn't have dipole-dipole interactions, and it doesn't have hydrogen bonds. So we can put nothing here in this box for dipole-dipole and nothing here for hydrogen bonds. Okay. So now let's go ahead and analyze fluoroethane. So here I have drawn fluoroethane molecules. There's one on the left and there's one on the right. So again, we have to figure out this is a nonpolar or polar molecule by looking at the polarity of the bonds. And so here, this hydrogen here has an electronegativity of 2.1. This carbon has an electronegativity of 2.5. This fluorine has an electronegativity of 4.0. So while the carbon-hydrogen bond here I'm pointing to is a nonpolar bond, the carbon-fluorine bond is a polar bond. And so maybe one of the things you might remember is that you can sort of represent the polar bond with a dipole moment arrow for the bond. And so this kind of reminds us that here, this shared pair of electrons in the bond is going to be spending a lot more time around fluorine than carbon. So if we want to, we can put a delta negative around this fluorine, and also the carbon here will be delta positive. Now, here you can look at the molecule on the whole. You can see that we have a polar bond to the right on this molecule, and there's not really one going to the left to balance it out. So this is going to be, the whole thing is going to be a polar molecule. So the right end of the molecule with the fluorine is delta negative, and then the left end is delta positive. And so if we want to, we can remind ourselves that the whole molecule is polar with a delta negative, delta positive end by, say, drawing an oval around it. And we can remind ourselves that this whole thing has a molecular dipole moment. So what applies for this fluoroethane molecule applies for this one as well. So here we have this fluorine, it's the delta negative end in the molecule. The other end is the delta positive end. And so what is going on here is when you have this attraction between the delta negative end of one polar molecule and the delta positive end of another polar molecule, this is going to be a dipole-dipole interaction. So we have just figured out that fluoroethane has a dipole-dipole interaction. So we are here. Now again, you probably know at this point that all molecules have dispersion. So fluoroethane has a dispersion interaction as well. And so now we want to ask, does the fluoroethane molecule have hydrogen bonds? And so it will have hydrogen bonds if you identify that the molecule has both a hydrogen bond donor on it and a hydrogen bond acceptor. So here, if I'm looking at this fluoroethane on the right, I see that there is a lone pair on a very electronegative atom, which is fluorine. So that would be a hydrogen bond acceptor. But the question is, are there hydrogen bond donors on the molecule? Well, you need a hydrogen bound to an electronegative atom. We have hydrogen bound to carbon. Carbon is not considered electronegative enough for that hydrogen attached to it to be a hydrogen bond donor. So although fluoroethane has a hydrogen bond acceptor, it has no hydrogen bond donor, and therefore it will not have any hydrogen bonds here, so I'm going to leave it blank. Okay, the last molecule we're going to look at is ethanol. And so all molecules, whether they're nonpolar or polar, have dispersion interactions, and so we can put a check mark here. So let's check to see if ethanol here has a dipole-dipole interaction. And so here, carbon has electronegativity of 2.5. I'm not going to write that here just to make this a little bit clearer. Oxygen has electronegativity of 3.5. So this bond here is actually polar. So we can put a delta negative around this oxygen here. If we wanted to, we can put a delta positive around the carbon. Now we have another polar bond from hydrogen to oxygen. So I'm drawing the bond dipole moment there. And so this is delta plus also, this hydrogen. And then the other end of the molecule is going to be delta plus. And so this is really a pretty polar molecule. So you can see you have one end that has delta negative, and then off to the side is delta positive. And then over here, it's not really balanced by this delta positive region over here. So this is really a polar molecule here. And so this other molecule here of ethanol also will be polar. And so here, the delta negative is around the oxygen here. There's a delta positive of this hydrogen, and there's a delta positive on this hydrogen as well. So there's going to be a dipole-dipole interaction because the delta positives of one ethanol molecule will get close to the delta negatives of another. And this is just one way it could be done. So this will have a dipole-dipole interaction. Okay, so the next question we have to ask is, does the ethanol molecule have hydrogen bond donors and acceptors? Well, so let's first look at the oxygen atom of ethanol, and you can see there are two lone pairs here. And so you can see that the lone pairs are on oxygen, which is a very electronegative atom. So this is a good hydrogen bond acceptor. Now, does this molecule also have a good hydrogen bond donor? So here we have hydrogen here, and it's attached to a very electronegative atom, which is oxygen. And so the hydrogen here is a hydrogen bond donor. Now, just to note, the hydrogens attached to the carbons do not count as hydrogen bond donors for the reason I gave you earlier. So hydrogen bonds can form between, say, the right ethanol molecule here on the left. And the way it happens is that the hydrogen bond donor, this hydrogen of one molecule, will be attracted to the hydrogen bond acceptor, the lone pairs around the oxygen on the other molecule. And same thing with this one over here, but this time it's going to be the lone pairs on this oxygen on the left molecule. The hydrogen bond acceptor will be attracted to this hydrogen bond donor with the hydrogen here being attached to the oxygen. So there are hydrogen bonds here. Okay. So at this point, we can order these molecules in terms of increasing melting point. So small molecules that are nonpolar like ethane only have dispersion forces. If they're small, there are not a lot of them. And so you don't need much heat to break up those interactions. And so this will have the lowest melting point. Okay, and so now we have fluoroethane. Fluoroethane is a molecule with dispersion forces, but it also has dipole-dipole interactions. And so it's going to have a moderately higher melting point. And then finally we have ethanol, which has dispersion forces, dipole-dipole interactions, and hydrogen bonds. And so this is an even higher melting point. And so that gives us the order which I have on the slide. Now, one thing I just want to quickly point out is here the melting point of this covalent molecule ethanol, which is relatively high for a covalent molecule, doesn't even compare to the melting point of an ionic compound. So I think you can see this on the slide that the melting point for ethanol here is negative 114 degrees Celsius, which is pretty cold, right? Now, if you had NaCl, an ionic compound, what would be the melting point for that? It would be 801 degrees Celsius. So again, just a reminder that ionic compounds here have extremely high melting points. Okay, thank you for listening to this presentation. We'll see you next time.